Welcome to Chapter 5 of Pre-Calculus 11. So this is the first video for this chapter. The chapter is all about radicals, which you'll find out what that means in this video. I did do a quick recap video before this one that covers prime factorization. So if you don't remember how to do prime factorization, if you haven't already watched that video, I would recommend going back and taking a look at that one, just so you'll be able to understand what's going on in this one. So, introduction to radicals. Well, the main thing to take away from this is going to be what's a radical. This might be something that you learned in grade 10, depending on who your teacher was and what you got through, but it's really going to be a main focus of this chapter. So a radical, in a really basic level, it's just a term involving a root of some kind. It might be a square root, might be a cube root. We can have variables, we can have numbers. We got lots of options, but long and short of it, it's going to be a term that has some kind of root. So it could look something like the square root of 12. Maybe you'll have a number out front like 2 root 3. Like I said, maybe a cube root, maybe a variable. These are all radicals. We can do lots of things with them. We're going to spend this entire chapter working with them. So to break things down a little bit, a radical will typically have 3 components. We won't necessarily see them all, but they are technically there. So first, and probably most importantly, is that thing on the inside. So I've labeled that C here. And so the thing in the inside of your root is called the radicand. And that's just whatever you're doing your root of. So up in our previous examples, square root of 12, 12 is your radicand. It's the thing you're finding the root of. B, in our example here, is what is called the index. And so you should have a good sense of what this does, because you have been seeing it ever since you started working with anything other than square roots. And so the index is just the thing that tells you which root to do. So if it's a 3, it's a cube root. If it's a 7, it's a 7th root. If there's nothing there, so for example, in that root 12 that we've got up there, the default is a square root. So a lot of times in math, if we don't see a number, the number that we don't see is a 1. In the case of the index, if you don't see an index, your index is 2 for square root. So that is an important thing to keep in mind. And then the number out front is an idea that you're familiar with because you've seen it a lot in this course and elsewhere. It's just a coefficient. Same as coefficients on variables or on anything else. So nothing new there. All right, so when we're dealing with radicals, there are 2 different ways that we can write them. And this is the thing that you probably would have seen in Math 10. So our radicals can be written as either mixed radicals or entire radicals. And so a mixed radical is a radical with a coefficient. So if you look back at those previous examples, we had 2 root 3. So this one here. So the 2 is a coefficient for our root 3. So that's a mixed radical versus these other 3 up here. Since they don't have coefficients, those are not mixed radicals. Our other option is called an entire radical. And that's just a radical that doesn't have a coefficient. So we're going to work with both of these quite a bit. They both have their advantages and disadvantages for doing different things. So this video is mostly going to focus on just moving between them. So if you want to use a specific form to do a specific thing, you might have to switch a given radical from mixed to entire or vice versa. So, for example, we have 3 root 5, and eventually we're going to be able to turn that into root 45. So the one on the top, that's our mixed, and the one on the bottom is our entire. So let's start by going from entire to mixed. Neither way is a particularly difficult process. It's something you'll get pretty good at, but we'll just start with this one. So let's say we wanted to convert the square root of 24 to a mixed radical. You can kind of think of radicals as being sort of like fractions. They're not, but they do have some similar properties. So converting this to a mixed radical is kind of like turning a fraction into a mixed number. Again, it's not, but it's just sort of the same thought process. So the first thing we need to do is to find the prime factorization of our radicand. So this is why going back and looking at that prime factorization video is going to be helpful. Thankfully, 24 is a pretty small number, so this shouldn't be too difficult to do. So we're going to take 24, and remember, we're just going to break this down in maybe a factor tree. So 24 breaks down into 4 and 6, 4 breaks down into 2 and 2, and 6 gets you 2 and 3. So our prime factorization for root 24 is going to be root 2 times 2 times 2 times 3. So we leave that thing inside the root. All right, so now to pull stuff out, we are going to start making some groups. Groups of the same thing. And this is actually very similar to something you probably would have done even back in grade 8 when you were learning how to do roots of numbers. So same sort of principle, you would have been making groups back then too. The one thing to keep in mind, there's going to be a difference between, say, a square root and a cube root or a fifth root. So whatever your index is, it tells you how big your groups are. So in this case, since this is a square root, we're going to be making groups of 2. But if it was a cube root, we'd be making groups of 3. So our root 24 is going to equal, like we said, root 2 times 2 times 2 times 3. And so if I look at that, I can make one group, one pair of 2s. The other 2 and the 3 I can't really do anything with because they're not the same thing. So I'm just left with this one pair. An important thing that's going to kind of be the basis of what we're about to do. If you have 2 roots with the same index, so say a square root of 5 and a square root of 10 or whatever, if you multiply those two things, you can just multiply the radicands together. So in my example here, the xth root of a times the xth root of b just gets me the xth root of a times b. Or, like I said, the square root of 5 times the square root of 10 just gets me the square root of 50. So we're going to kind of use that idea in reverse. We're going to take our root here, and I'm going to break this down probably more than I would actually do it myself when I was doing a question. And we're going to split that root up into 2 roots. So we've got root 2 times 2 times 2 times 3. And using that important thing in reverse, we're going to break this up into root 2 times 2 and root 2 times 3, because it's just a bunch of stuff being multiplied together. And remember, we've still got that group of 2's. And so 2 times 2, well, that's 4, right? And 2 times 3, that's 6. But we know what the square root of 4 is. The square root of 4 is just 2. And so what we're left with is 2 root 6. Those 2 steps over here, so this and this, these are really not steps that I would ever actually show. So what we really do is once we've got that group of 2's, we're going to go straight from there to here. And what we do is we pull out one value from each of the groups. So when you make a group of 2's, you're going to pull out that group of 2's and they kind of get condensed into 1, 2. And there you have it. We have ourselves a mixed radical. So let's try it with a bigger number so we can see this process a little bit better. So let's say we're going to write, let's say root 540 as a mixed radical. So same deal, we're going to have to do prime factorization. So 540, I can see that's got a 0 at the end, so I'm going to break it up into a 10 and a 54. 10 is going to get me a 2 and a 5. 54, probably a 6 and a 9, which gets me a 2, a 3, and a couple more 3s. So root 540 is root 2 times 2 times 3 times 3 times 3 times 5. And if you're ever not sure, remember you can just multiply all those back together to make sure you actually got 540. So looking at this, we've got a pair of 2s, we've got a pair of 3s, and then that 3 and that 5 just kind of hang out at the end. So this pair of 2s is going to condense into 1 2 that's going to be on the outside of the root. Same thing for the pair of 3s. So we're going to have a 2 and a 3. And then that 3 and that 5 are just going to stay inside the root because we can't do anything with them. And so if we just multiply together what we've got here, this gets me 6 root 15. And again, this is really easy to check. If you just plugged root 540 into a calculator, you're going to find out that it's got a value of, give or take, 23.24. And if you do 6 times root 15 in a calculator, you're going to get that same 23.24. So really, really easy to check up on if you're using a calculator. Granted, if you're in my class for this chapter, you are probably not going to be allowed to use a calculator because I don't want you just getting a calculator to tell you what to do. I want you to show me that you know how to do it yourself. So something to keep in mind. All right, so try doing this one yourself. So write the fourth root, keeping in mind what I said, so fourth root of 64 as a mixed radical. So if you're not sure how to handle that index, that 4, just scroll back up, look at what I said about the process, and then see what you come up with this one. It shouldn't be too bad. All right, so if we take that 64 and we break it down, 64 is just a whole bunch of 2s. Specifically, it is 6 2s. So if I want to do a fourth root, previously we said that if your index, well, whatever your index is, that's what's going to tell you how big your groups are going to be. So since this is a fourth root, I'm not going to make a group of 2 2s, I'm going to make a group of 4 2s. And so all 4 of those 2s, when they come out of the root, are just going to get condensed into 1. And then inside that root, I've still got a couple of 2s. And so that 2 times 2 is going to get me a 4. So this becomes 2, and then the fourth root of 4. Do be careful when you're writing things, by the way. You might notice it's kind of hard to tell whether that's a 2 to the power of 4 or whether it's a fourth root. And I kind of did that intentionally here. So generally, try to leave a little bit of a space and make sure that your index is like really snug up against the root like that. So that you can tell that this, oh, okay, that's a 2, and then it's a fourth root. All right. A couple of specific cases to think about. So if I've got the cube root of 8 or the square root of 10, let's talk about those. So 8 is also just a bunch of 2s, but only 3 of them this time. And 10 is a 2 and a 5. So for this one on the left, I'm making a group of 3 2s, which is everything. So those 3 2s are going to get condensed into a 2 on the outside, and there's just nothing left inside the root. So technically, you could leave this as, say, 2 cube root of 1, but that's really no good. We don't want that, so it's just 2. It's fine. For the one on the right, we don't have anything to make a pair of, and so this is just going to go back to 10, and it just stays there. We can't simplify this one. This one can't become a mixed root. Think of it like a fraction that you can't simplify. If it's like 3 over 7, it doesn't simplify, it just is what it is. Okay, but what if there's variables? So what if we had, for example, the cube root of 56, and then we had a y to the power of 8 in there. So the 56 is the same as whatever it is. We're not going to have to think too hard about that. So 56, I'll just tell you, is 2 times 2 times 2 times 7. Okay, not too bad. By the way, be careful that you don't drop your index halfway through a question. It's a really common mistake. So if it starts as a cube root, make sure it stays as a cube root the whole way. For the y's, there's two ways you can go about doing this. One option is to just take that y to the power of 8 and break it up. Y to the power of 8 is a bunch of y's multiplied together, specifically 8 of them. So it becomes y times 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 y. And so we got all of that inside of our root. So we're going to split up the variable. And this works. And so now you're just going to do it the same way we do the other ones. We're doing a cube root, which means we want groups of 3. So I got 3 2's, I got 3 y's, I got 3 more y's. And so outside my root, I'm going to have a 2 and a couple of y's. Inside my root, I'm going to have a 7 and also a couple of y's. Which is going to leave me with, as my final answer, 2y squared cube root 7y squared. And that works. A slightly maybe faster and less time consuming and annoying way of doing it is also to just say, okay, I'm going to be making groups of 3. So if I've got y to the power of 8, I can make 2 groups out of that. And then I'm going to have 2 left over, right? So 2 groups would get me 6. And then with 2 left over, those 6, you're going to divide by 2. Or sorry, divide by 3 because we're making groups of 3. So 3 goes into 8 2 times with 2 left over is another way of thinking about it. It's up to you. It doesn't really matter. Okay. Adding another little layer onto this. You might be asked something along the lines of, write 3 root 75 in what we'd say simplest form. So what simplest form means is just everything pulled out. So this already is a mixed radical. There is already that 3 on the outside. But when I say simplest form, I mean I can keep going. I can do a little bit more. So if we take this, our 3 root 75, we're going to kind of just ignore the 3 for now. So 75 is going to break up into 3 and a couple of 5's. We're going to make a group of 5's, same as usual. So if we ignore this 3, if we pretend it's not here, then what we'd have is we'd have a 5 coming out of our root, and we'd have a 3 left on the inside. So remember, if you have a coefficient out front, like we do here, that just means multiplication. This is 3 times that root. And so it's still 3 times whatever we had there. And so if you look at this now, 3 times 5 root 3, well, really, we can just do 3 times 5. We're just going to take that thing on the outside, we're going to multiply those, and we're going to get 15 root 3. So if you pull anything out of a root and there's already something on the outside, you just multiply whatever's already out there with what you pulled out. So it's not too much more difficult. So see if you can apply that to this next one on your own. So we're going to have 10 cube root of 72. So give this one a shot, come back, we'll do one more quick one, and then we're going to try going the other direction. Okay, so the 10's just sitting there. 72 is some 2's and 3's. Specifically, it's 3 2's and a couple of 3's. So looking at that, I can make one group of 2's, which is going to get me 10 times 2, and then cube root 3 times 3. So that 10 and the 2 is going to make me 20, and that 3 and that 3 is going to make me a 9. So we get 20 cube root 9. One thing I wanted to touch on before we switch to the other way, there is another way to convert from entire to mixed, which relies on having a pretty good sense of numbers and factors and perfect squares. So if I look at a number like, say, root 360, and I want to convert that. So instead of doing prime factorization, what you can also do is look at the number and think if there are any perfect squares that you can recognize that go into this thing. So 360 is divisible by 4, divisible by 9, but it is also divisible by 36. So this we can split into a 36 and a 10, right? And so if I break those up, this becomes root 36 and root 10. Well, root 36 is just 6, and 10 is just 10. And so this becomes 6 root 10. And so instead of having to do prime factorization, I was able to break that up pretty quickly. And so that is just a slightly different way of doing this. I wouldn't recommend it most of the time, but just know that it is an option. All right, so now we want to go from mixed to entire. And this is generally a little bit easier. It doesn't require as much process. There's no prime factorization or anything here. So let's say we wanted to convert 3 root 5 to an entire radical. We're basically just going to undo our process from before. So in the previous ones, looking back up here, we would take a group, condense it, and move it out. So what I want to do is I want to take that thing on the outside, and I basically want to turn it back into a group of things. So my first step, we're going to put the coefficient into a root, and we're going to do that using exponents. So our 3, if we put that back into a root, well, that becomes 2 3s, right? So we want a pair of 3s, which is going to condense into 1 3 on the outside. Which is, if we think about it, 3 squared, or we can also say 3 is really just the square root of 9. And that is something we do know, right? 3 is the square root of 9. Makes sense. So we're going to use that exponential form, that 3 squared, as kind of our intermediary step. So what we'd do is we'd say, so 3 root 5 is going to become the square root of 3 squared times the square root of 5. And this is where that important thing from earlier, where we can multiply 2 roots by just multiplying the radicands, comes into play. So step 2 here is just multiply. So our root 3 squared times root 5 is just going to become root 9 times root 5, which is root 9 times 5, which gives us root 45 as our answer. And that's way more time consuming than it actually needs to be. You can skip showing a lot of those steps. So really what you need to do to look at this is you say, okay, root 3 times 5 is root 3 squared times 5, which is root 45. And that's really the process by and large. So if we try another one here, say we wanted to do, I don't know, 4 root 2. And I wanted to turn that into an entire radical. So I want to move that 4 inside of a root. So it's going to become 4 squared times 2, which is going to become, well, 4 squared is 16. So it's 16 times 2, which just gets me root 32. You might be asking yourself what happens if it's not a square root, and that is a pretty easy thing to handle. So it's if we had, say, 5 cube root of 28. So if I want to move that 5 into a cube root now, remember we need to have a group of 3 5s. And then we still have that cube root 28. Well, 3 5s, if we simplify that a little bit, becomes 5 cubed inside of a cube root. So all you really need to do to adjust for the fact that it's not a square root is your index has to match your exponent. All right, so those two things are the same. And away you go. So if we calculated this, 5 cubed is 125. and then we just have to multiply that by 28. And if you go through and do that, you'll find out that 125 times 28 is 3,500. What if there's variables? Let's try that out. So let's say we had 2x squared and then cube root 3x. Go ahead and give this one a shot for yourself. It's a little bit beyond what you've seen, but you should have hopefully all the skills you need. You might have to think back to your exponent laws a little bit, but give it a shot and see how it goes. All right, so this is a cube root. So if I want to move that 2x squared into a root, I'm going to have to cube it. And so that's really the tricky part of this one. We've got to think about what that means. So if I want to do 2x cubed, or 2x squared rather, cubed, so a couple of exponent laws are coming into play here. First, when you have a product, so 2 times x squared, being raised to a power, that power goes onto both of those things. So this is going to become 2 cubed, and then it's going to become x squared cubed. Secondly, if you have a power raised to a power like this, so you've got x squared cubed, you're going to multiply those exponents. So this is going to become 8, and then x squared cubed is going to become x to the power of 6. So back over to the left side here, we've got our cube root of 8x to the power of 6 times our cube root of 3x. And now we just multiply those things. So 8 times 3 gets me 24. And remember, when you multiply two powers like this, you're going to just add the exponents. So x to the power of 6 times x is going to get me x to the power of 7. And all of that's inside of a cube root. Okay, last quick example. We can use this to compare roots. So let's say you were asked to figure out whether something was bigger or smaller, or to put some things in order. So we're going to put some terms in order from smallest to largest. So we've got 2 root 5. We've got root 15. We'll throw a 3 in there, so just a 3. And then negative 4 root 2. So most of these are pretty simple to deal with. The one thing to keep in mind, if we're going to compare roots, we can't really easily compare mixed radicals. So if you look at 2 root 5 versus root 15, without using a calculator, there's not really a clear way to know which of those is bigger. But we can compare entire radicals pretty easily. If you have a root 7 versus a root 8, you know root 8's bigger. So we're going to compare as entire radicals. So if we take that 2 root 5 and we convert it to an entire radical, that's going to become 2 squared and 5, which is going to get us root 20. The root 15 is already entire, so we don't have to think about that one too much. 3, well, that's just the square root of 9, so we can just pop that one right in. But if you want to think about it, it's basically just 3 squared. And then the 4 root 2, or specifically the negative 4 root 2. So negatives, when it comes to mixed and entire radicals, are a little bit tricky. If it's an even index like it is here, we can't move the negative inside the root. So remember, you can't do a root of a negative number, or at least you can't do a square root of a negative number. If it's a cube root, a fifth root, then we can move it inside. It's not going to be something we're going to deal with too much, so I'm not going to spend a bunch of time on it here. So for now, just know that we need to leave that negative on the outside. So this becomes negative root 4 squared root 2. 4 squared is going to get me 16, and 16 times 2 is going to get me 32, but we still have that negative on the outside. So putting these in order, well, the negative one's definitely going to be the smallest. So our smallest is negative 4 root 2. I'm going to rewrite them back in their original forms. And then looking at the others, 9, 15, and 20, well, 9's my smallest radicand. So my next smallest one is the 3. Then it's the root 15. And then lastly, it's the 2 root 5. And there we have it. We have put them in order from our smallest to our largest. And now you should hopefully have a pretty good sense on converting from mixed to entire radicals and back again. The rest of the chapter is going to use these skills pretty heavily, whether you're adding or subtracting, multiplying or dividing, whatever. The one thing to keep in mind when you're comparing like this, we can't compare square roots and cube roots, so don't even bother trying. They don't really mix. We might see the occasional situation where we can kind of force things, but by and large, square roots and cube roots just kind of work separately, and ditto fourth roots or fifth roots or whatever. So now that you've got a good sense on how to convert these things, go ahead and take a step forward and look at how to add or subtract or multiply or divide and see how you do.